Hello, my name is Ashwin and I am a PhD student at Georgia Tech. I am presenting our work on using event and frame vision together for high speed and high accuracy optical flow calculation for edge platforms. The video shows a recording from a frame camera along with the optical flow computed on it. Optical flow finds application in video stabilization, odometry or feature tracking like tasks. Conventional model-based approaches use gradient matching across two frames to identify the motion of the objects within the frame. These algorithms typically require multiple matrix inversion kernels along with frequent memory accesses. Convolutional neural networks, or CNNs, offer more accurate predictions but have prohibitively large number of operations to calculate for a real-time application. This becomes even more difficult when we have an edge platform with constrained resources, like in any typical robotic application. Even if faster compute is available, the speed gets eventually limited by the frame rate of the camera. Therefore, frame-based optical flow has high accuracy but lower speed on edge platforms. A more recent sensor, called dynamic vision sensor or event camera, shows a way to circumvent this low speed issue. Event camera provides asynchronous events instead of discrete frames. An event is generated when the intensity of a pixel changes. For example, assume this to be a rotating disk with a dot on it. A frame-based camera would capture something like this where you have discrete frames, but event camera would capture a continuous stream of events. They also have additional advantages of low power. Accumulating events within a time window and then applying the well-known algorithms, the frame-based algorithms on them is possible. But then the issues of computational complexity of the frame-based algorithms get carried over. Spiking neural networks have been used here, but they typically have lower accuracy because of lack of reliability in training. On the other hand, neurobiological findings have been used in some networks. A correlation-based optical flow computation in insect brain has been hypothesized long ago. This model says that there are neural filters tuned to a direction of the motion in the brains of real organisms. Assume the movement in this direction. This neuron receives activation first, followed by this neuron at a delay of delta. If the connection from neuron 1 to the output neuron has a delay of delta, then the activity generated at these two neurons would reach at the output neuron at the same time, causing a high activity. Whereas if the direction of motion is opposite, then there won't be activity at output. So this pair of neurons along with the output forms a tuned filter which is tuned to the direction of motion in this way. This was recently shown biologically plausible by probing the neurons in a fly brain. And this kind of a model has been applied on SNNs for simple custom datasets previously. However, their accuracy is low and therefore simple datasets have been used. So event cameras and event-based pipelines provide a way for fast processing but is limited with the accuracy. So we have two sensors and processing pairs for high accuracy and high speed. The frame-based pipeline captures detailed spatial description of the scene and provides a high accuracy. The event pipeline has finer temporal resolution, capturing minute temporal details for high speed of processing. Our proposal is to use these two in parallel with fusion of outputs from both pipelines. The event pipeline provides multiple high-speed predictions and they are periodically fused with frame inferences to monitor error. Thus, the overall fused output has high frame rate but a correction mechanism to keep the accuracy high. The frame pipeline works with a gradient-based conventional optical flow algorithm shown here as span-back flow. For the event pipeline, we build a leaky CNN filter that uses biological filter structures from previous slide. This slide describes the structure and function of the leaky filter. The first layer works as asynchronous leaky accumulator. The event stream comes in with x and y values for a pixel it corresponds to. Layer 1 adds the incoming pixel to the activation of the layer. There is also a term for leakage, which is shown here as alpha, which causes the contribution of the previous events to go down. Alpha basically controls the leakage factor. The event accumulated frame, by accumulating events in the layer 1, is shown here. The timestamps of the incoming events inherently store the information about the direction of motion. It is from high activation to low activation, that is from the recent event to previous events. The second layer has differential kernels which are implemented as excitatory and inhibitory synapses. The difference in activation of adjoining pixels is calculated for every pixel. This provides a local flow value for each of the pixels. This is carried out for both vertical and horizontal directions as shown. The noise in the event stream makes this output highly granular. Therefore, this local flow, as shown here in this figure, is highly noisy as it can be seen. Therefore, we need an averaging filter, which is the layer 3 for the spatial continuity criteria. The smoothened flow can be seen here, where the direction of motion for the drone is identifiable. We color code the horizontal and vertical optical flow directions for easier visualization as shown here. The first layer operates continuously, but the other two operate only when triggered. They are triggered after a fixed duration, that is called epoch, which determines the frames per second or throughput of the event pipeline. In principle, this can be arbitrarily fast because there is no restriction from the sensor side on the frame rate. The restriction is put by processing speed of layer 2 and layer 3 in hardware before we trigger them again. So this is only compute limited and not sensor limited. The output of the event pipeline is noisy and requires correction from the frame inference. This is carried out using the fusion algorithm that we propose. The algorithm checks for consistency in event and frame outputs in both spatial and temporal dimensions. These are the outputs from both pipelines to start with in this example that we have. The fusion algorithm is required to do two tasks. One is to compensate the erroneous pixels in the event flow, and secondly, if there is an external moving object that has not yet been processed by the frame pipeline, the fusion algorithm has to identify that region and not correct it using the frame flow. This is carried out as shown. The fusion algorithm first checks if the outputs differ in the both pipelines significantly. This shows abrupt change between frame and event outputs. This indicates that a possible presence of an external moving object. However, event pipeline is noisy and abruptness may just be because of the noise. Thus, in second criterion, which is shown here, it checks if the event inference is consistent with the previous event inference. If so, there is a high chance that anomaly is because of the external motion. If both these conditions are satisfied, this indicates that the abruptness may be because of an external moving object. These pixels are identified and mapped as uncertain pixel map as shown here. The uncertain pixel map is spatially averaged. This provides the regions with possible uncertainty. If same regions appear again and again in the uncertainty map over multiple inference times, this provides a temporal consistency for an external object. Therefore, a confidence map is created for every pixel using the spatiotemporal continuity criteria. The points with high confidence score indicate a presence of an external object which needs to be taken from event pipeline, and the other pixels should be taken from more reliable frame output. Therefore, this decides whether to use the final fused output pixel from frame output or event output. This is shown as pixel assignment here. The green pixels are taken from event pipeline, whereas the pink pixels are taken from the frame pipeline's output. The fused flow is calculated by using outputs from the both pipelines, and fused output is compared with the ground truth for error calculation or average endpoint error calculation to see the robustness of the method. The algorithm is first validated on MVSEC dataset that has both event and frame recordings for a drone flight. This is the event accumulated layer 1 and optical image from both cameras, and the event and frame flow output for the both. We calculate the uncertain pixels regions and the confidence map for the two pipelines and assign the pixels as shown here. There are no external moving objects in this video, but still we see some events assigned from the event pipeline. That is because the abruptness criteria is kept very relaxed for illustration purpose. The algorithm is now validated on MVSEC dataset and will move on to the results section now. There are multiple parameters within the algorithm that need to be tuned for optimal performance. The criteria for using a pixel from the event pipeline is repeated here from the previous slide. Naturally, if these thresholds are relaxed, more contribution from event pipeline would be added in the final fused flow. This is shown in this figure. More contribution of event pipeline also induces more noise in the final output. Say we use thresholds from point number 1. The relative FPS of the event pipeline is shown here. This means 5 epochs of event pipeline are processed within every processing of frame pipeline. Higher relative FPS means less number of events to be processed in every epoch because the epoch duration gets smaller. Therefore, the error rate is expected to rise as the relative FPS of the event pipeline rises. This is shown in this figure. Each of these lines corresponds to one sequence in the MVSEC dataset. The error monotonically rises with rising contribution of the event pipeline. So relative FPS and event pipeline, the percentage of events from event pipeline rise together. Although the event pipeline is faster than frame pipeline, it cannot be made arbitrarily fast in order to avoid error degradation. Finally, the speed versus error trade-offs for both pipelines is shown in this figure. This yellow point corresponds to the frame pipeline with low error and low speed. The blue point corresponds to the event pipeline, which has both high speed but high error. The fusion mechanism allows us to trace this trajectory in between for mitigation of this trade-off. With fusion, the FPS remains high, but the error rate gradually comes down. Therefore, the speed versus error trade-off is mitigated using the fusion algorithm. At relative FPS of 4, which is shown at this point, it shows a reasonable degradation of error rate. Assuming 30 FPS to be the speed of the frame pipeline, this point requires the hardware for event pipeline to work at 120 FPS. Validating this is the next step of our work. We map the network on edge FPGA of Zinc family. The microarchitecture is described here. The first layer keeps processing for every incoming event using a block RAM. The layers after that, layer 2 and 3, are triggered after every epoch. The contribution given, the computation gives the output of the event pipeline, which is shown here, which is stored in DRAM. This is fused with the event and frame outputs of the previous processing event that were stored in DRAM. The uncertainty region and confidence map is calculated one after the other to assign pixels and finally calculate the fused flow. Mapping this using Vitess high-level synthesis shows a FPS of 118, which is close to 120 that we envision, and that this shows the feasibility of using this for using this kind of a fused system on a constrained platform. Please refer to the paper for more details about hardware mapping. We compare the previous approaches calculating optical flow over MVSEC dataset in this table. These references mostly use convolutional neural networks like UNet and similar architecture. The speed is therefore limited by the number of computations. The high speed in some cases, as shown here, is possible on GPU with huge resource availability. Our system is implemented on a Zinc FPGA, which has an energy budget of less than 10 watts. We show speed and accuracy of the similar order, as shown here in this table, on this constrained platform using this multimodal bio-mimetic fusion approach. The exploration so far was to make sure that the hardware capacity and algorithmic correctness of the system is good. The application requires an external moving object that is difficult to be tracked in real time on a frame-based system. We demonstrate such an application here. We fly a prey drone manually in front of a Davis 346 camera in indoor lab setting. The video is shown here. The recorded data is passed through the algorithm. This is the frame output and this is the event output. Between every two consecutive frame outputs, you can see there are multiple outputs of the event frame showing the high FPS of the event pipeline. The uncertainty region is calculated here. The uncertain region is shown to have a high value where the drone is actually flying, and therefore what it does is it causes the event pipeline to contribute to the region where the drone is flying, which is this region, and the background is primarily fused from the frame pipeline. The interesting thing to note is that event pipeline calculates multiple correct optical flow outputs even before the frame pipeline has even seen the change of direction of motion because of the limited frame rate of the frame pipeline. Further applications of this system on high-speed tracking-like applications are possible. To conclude, we show a multimodal sensor processing system which gives us both high speed and high accuracy simultaneously using complementary prowess of the event and frame pipelines. We verify the system on MVSEC dataset and also apply it to a real drone flight scenario along with the hardware feasibility checks, which shows a possible FPS of more than 100. This shows that fundamental trade-offs in frame-based processing can be mitigated using data processing from other complementary pipelines. We would like to thank IARPA for supporting this research. These are the key references used in this. Thank you very much.